E. Hello, my name is Henry.
Hello, everyone. My name is Zach, and this is our final presentation for CS 253 class, and our topic is PageRank. So to start off, what is a PageRank? PageRank was the first search algorithm implemented by Google, which is a big name. As you can see in the picture to your right, Google used to have a number inside of their toolbar that shows the weight or the importance of a page, which is the PageRank. So PageRank basically is a algorithm that rank web page in the search engine result, which is used by Google. And it's a way to evaluate the importance of the website. It's named after one of the co-founder of Google, Larry Page. And basically, a PageRank score is the quantity of the links that's linking to the web page and the quality of the links that's linking to the web page. And we add the two components together to calculate the PageRank score for the web page.
Next, I'll be talking about the motivation. So why should we care about PageRank at all? First of all, it provides web users, which is us, with more accurate search results. Secondly, it decides what results to show at the top of the search engine listing based on the PageRank of each web page. And finally, it prioritizes websites that are more frequently linked to and are more likely to present relevant information. So as you can see from these reasons why Google should really prioritize this algorithm, as Google is a huge company known for its optimization of its search engine. So now I will go to an in-depth explanation of the PageRank algorithm. One central assumption of the PageRank algorithm is that a page with high importance would have more important links pointing to it, which means that we evaluate the PageRank of a web page not only by the quantity of the links pointing to it, but also the quality of these links. In a paper written by Ian Rogers, he states that PageRank can be calculated using a simple iterative algorithm and corresponds to the principal eigenvector of the normalized link matrix of the web. Well, this sentence may seem very confusing. In this final slide that we present, we're actually simply going to be looking at a more elementary understanding of the PageRank algorithm, and which can be understood by a single and central equation as seen from the right side of the slide, right here. In this central PageRank equation, it states that, as you can see, we can calculate the PageRank of a particular node or a particular web page by summing up the PageRank of all of its innodes or parent nodes, and dividing by the amount of parent nodes that it has, or the out degree of the particular node. And from there, we will multiply this by 1 minus the damping factor. So what is the damping factor? I'll have to explain from another perspective of looking at the PageRank algorithm. So the PageRank theory holds that an imaginary surfer who is just randomly clicking on links will eventually stop clicking. And the probability that this imaginary surfer will continue at any step in this situation is the damping factor. So the damping factor is actually the probability that the imaginary surfer will continuing surfing the web. And the d divided by n, this term is called random walk. And in a later slide, I will go more in depth in explaining what this term means. But at this point, you'll see how this term actually damps down the importance of the sum of the PageRank of the parent nodes. So this stops from the other page of having too much influence over the PageRank of this particular node. So as I explained before, the implementation of PageRank is simply putting this central equation into code. So the algorithm steps are as listed below. First of all, we will initialize the page rank of every node with a value of 1, which is fairly straightforward. We're simply initializing each variable. And second of all, for each iteration, we'll update the page rank of every node in the graph. So as I explained previously, this equation will only calculate the page rank of one specific node or web page at one particular time. And in order to calculate a PageRank score for all of the nodes or websites, we will simply do multiple iterations of the equation and update the PageRank of every node in the graph. Then the new PageRank is the sum of the proportional rank of all of its parents. This is also can be seen from the equation. So the proportion simply refers to this term, 1 minus the damping factor. And after that, we apply random walk to the new PageRank. Well, random walk might seem like a technical jargon. It's actually fairly straightforward, and it simply refers to this term, the damping factor divided by the number of nodes in total. So as I previously said, the damping factor refers to the probability that the imaginary surfer will continue clicking on web pages. And so you divide that probability by n, and you get the probability that the imaginary surfer will wander or click on and be on any of one of the web pages randomly. And finally, as I said, after enough iterations of performing the central equation, we'll simply get a converged value of PageRank for each node, and that's when we will stop the iterations. So shown on this slide is a Python implementation of the PageRank algorithm, and you can actually see quite clearly that this code simply follows the steps that I said on the previous page, and it's simply putting this mathematical equation into Python code. So to start off with, we initialize all the variable values to 1 for empty lists, arrays, and then this is a one iteration of the equation of the central PageRank equation. And as you can see, this is literally just this equation put into Python code with the summation value being represented by a for loop, and random walk is the damping factor divided by n, and everything else is fairly straightforward. And then, as I said, to calculate the converged PageRank value for each node, we do the update. We call the update PageRank function for each node in the list. So every single web page that we have, and we perform multiple iterations until it converges to a specific value.
Okay, so here's the first example we brought to you guys to visualize how PageRank work. As you can see in the picture, there are in total 6 nodes, and node 1, which is website 1, has the lowest PageRank score, and node 6 or website 6 has the highest PageRank score. The reason for this is if you only look at node 1 alone, there is no other page that's contributing to its PageRank score or to its importance. However, if you look at node 6, all of the nodes are contributing a portion of their importance to node 6, which is a cumulative score. So that's why node 6 has the highest PageRank score. So here is another example we brought to you guys to see if you can figure out yourself which node would have the highest PageRank score. I'll give you guys like 20 seconds to think about it. All right, so from the result, we see node 1 and node 5 have a relatively larger PageRank score or higher PageRank score than the rest of the nodes. The reason why node 1 is higher than the PageRank of node 5 is really simple. So if you look at node 1 alone, there are in total of 4 nodes that's contributing to its importance. And if you look at node 5, there's also 4 nodes contributing to its importance. So why is there a difference? If you look at node 1 closely, the nodes that is contributing to its importance are node 6, node 3, node 2, and node 5. And if you look at 5, the nodes that are contributing to its importance are node 6, node 4, node 7, and node 1. However, if we only look at node 6 and 7, they only have one node that's contributing to the importance of 6 and 7, which make them has a relatively weaker or lower PageRank score, which means they would not contribute as much of importance to node 5 as node 2 and 3 due to contributing its importance to node 1. It sounds really complicated, but if you break it down, node 2 and 3 all have 3 nodes that's contributing to its importance, but node 6 and 7 only have 1 node that's contributing to their importance. So that makes node 2 and 3 has a higher PageRank score than node 6 and 7, which in turn would make node 2 and 3 a more powerful or more important child to its parent than node 6 and 7 as a child to their parent, which is node 5. And that is why node 1 has a higher importance than node 5, even though they have the same number of links linking to them. So the runtime analysis for PageRank is pretty straightforward. We have V, which is the number of nodes, and E is the number of edges. So when we are first calculating the PageRank for one node, we're gonna use the number of E, which is the number of edges, or in other words, it's the number of child node that is contributing its importance to the parent node. And we're gonna repeat that process for V times, which is the total number of nodes in the graph or total number of related web page in the search engine. That's why we have a big O, V times E as the runtime.
So these are the references that we use to complete this final project, which includes a citation from a scholarly paper written by Ian Rogers, who gave a very thorough explanation on how the Google PageRank algorithm works, and a deep dive into the central equation itself. And he gives a very good explanation on each of the variables, and also gives a demonstration on how the PageRank algorithm is supposed to run. So thank you guys for listening to our final CS 253 presentation.
Thank you guys. Take care.